Hello everybody, electromagnetic pulse EMP. Moment please.
Chapter 4. Table of Contents 2. Table of Contents. 11. Sponsor/monitors report numbers. 12. Distribution/availability statement approved for public release, distribution unlimited. 13. Supplementary notes. 14. Abstract. 15. Subject terms. 16. Security classification of. 17. Limitation of abstract same as report, SAR. 18. Number of pages 208. 19A. Name of responsible person A. Report unclassified B. Abstract unclassified C. This page unclassified. Standard Form 298, Revelation 8 to 98, prescribed by ANSI STDZ 39-18. Report of the Commission to assess the threat to the United States from electromagnetic pulse, EMP, attack. Critical national infrastructures. Commission members Dr. John S. Foster, Jr. Mr. Earl Gell, Dr. William R. Graham, Chairman. Dr. Robert J. Herman, Mr. Henry, Hank, M. Klupfelgen, Richard L. Lawson, USAF, Rhett, Dr. Gordon K. Soper, Dr. Lowell L. Wood, Jr. Dr. Joan B. Woodard. April 2008. Critical National Infrastructures. Table of Contents 2. Table of Contents. Page. Preface. 6 Acknowledgements. 9 Chapter 1. Infrastructure Commonalities. 1 SCADA Systems. 1 Impact of SCADA Vulnerabilities on Critical Infrastructures, Historical Insight. 6 Infrastructures and their Interdependencies. 9 Commission-Sponsored Modeling and Simulation, MNS, Activities. 13 Summary. 15. Recommendations. 16. Chapter 2. Electric Power. 17 Introduction. 17 Description. 20 Vulnerabilities. 29 Test Results. 37 Historical Insights. 41 Distinctions. 43 Strategy. 45 Recommendations. 53. Chapter 3. Telecommunications. 62 Introduction. 62 Telecommunications support during emergencies. 64 EMP impact on telecommunications. 65 Recommendations. 79 Chapter 4. Banking and Finance. 83 Introduction. 83 The Financial Services Industry. 85 Vulnerability to EMP. 88 Consequences of Financial Infrastructure Failure. 92 Recommendations. 94 Chapter 5. Petroleum and Natural Gas. 95 Introduction. 95 Infrastructure Description. 95 Direct Effects of EMP on Petroleum and Natural Gas Infrastructure. 98 Petroleum Infrastructure and SCADA. 98 Natural Gas Infrastructure and SCADA. 99 Effects of an EMP event on the U.S. petroleum and natural gas infrastructures. 100 Indirect Effects of EMP, accounting for infrastructure interdependencies. 102 Recommendations. 103 Chapter 6. Transportation Infrastructure. 105 Introduction. 105 Long-Haul Railroad. 106 The Automobile and Trucking Infrastructures. 112 Maritime Shipping. 116. Critical national infrastructures. Table of contents 3. Commercial aviation. 122 recommendations. 127 Chapter 7. Food infrastructure. 129 Introduction. 129 Dependence of food on other infrastructures. 129 Making, processing, and distributing food. 130 Vulnerability to EMP. 132 Consequences of food infrastructure failure. 134 Recommendations. 137 Chapter 8 Water infrastructure. 139 Introduction. 139 The water works. 140 Vulnerability to EMP. 142 Consequences of water infrastructure failure. 143 Recommendations. 146 Chapter 9 Emergency services. 147 Introduction. 147 Emergency services systems architecture and operations. 147 Impact of an EMP attack. 149 Recommendations. 156 Chapter 10 Space systems. 158 Introduction. 158 Terms of reference for satellites. 159 Line of sight exposure to a nuclear detonation. 159 Persistently trapped radiation and its effects. 161 Nuclear weapon effects on electronic systems. 162 Satellite ground stations. 167 Discussion of results. 168 Findings. 170 Recommendations. 171 Chapter 11 Government. 172 Introduction. 172 Maintaining government connectivity and coherence. 172 Recommendations. 172 Chapter 12 Keeping the citizenry informed, effects on people. 176 Introduction. 176 Impact of an EMP attack. 176 Recommendations. 181 Appendix A. The Commission and its Charter. A1 Organization. A1 Method. A2 Activities. A2 Appendix B. Biographies. B1 Critical national infrastructures. Table of contents 4. List of figures. Page. Figure 1 to 1. Typical SCADA architecture. 2 Figure 1 to 2. Generic SCADA architecture. 3 Figure 1 to 3. PLC switch actuator. 4 Figure 1 to 4. EMP simulator with test structures and internal electronics. 5 Figure 1 to 5. Some of the electronic control systems exposed in test facility. 6 Figure 1 to 6. Physical model used to quantify coupling to different cable lengths in a hypothetical local area network, LAN. 7 Figure 1 to 7. A conceptual illustration of the interconnectedness of elements contained within each critical infrastructure. 12 Figure 1 to 8. Interdependency for anticipated network of the future. 14. Figure 1 to 9. Results of a model simulation. 15. Figure 2 to 1. Power system overview. 21 Figure 2 to 2. NERC interconnections. 25 Figure 2 to 3. GIC damage to transformer during 1989 geomagnetic storm. 33 Figure 2 to 4. EMP simulator. 38 Figure 2 to 5. Test item, electronic relay. 40 Figure 2 to 6. Flashover observed during injection pulse testing. 41 Figure 3 to 1. Generic telecommunications network architecture. 66 Figure 3 to 2. September 11, 2001, blocked call rate, cellular networks. 70 Figure 3 to 3. Example network management facility. 71. Figure 3 to 4. Cellular base station equipment. 72. Figure 3 to 5. Routers collecting network management data. 72 Figure 3 to 6. Cellular network testing at INL. 74 Figure 3 to 7. Testing at Notes facility. 74 Figure 3 to 8. Secure access card and cell phones. 75 Figure 3 to 9. Percentage of calls completed immediately after EMP event. 76 Figure 3 to 10. Percentage of calls completed 4 hours after EMP event. 76 Figure 3 to 11. Percentage of calls completed 2 days after EMP event. 77 Figure 3 to 12. Percentage of calls completed at time t, logarithmic time scale, within EMP contours. 77. Figure 5 to 1. Petroleum infrastructure. 96. Figure 5 to 2. Natural gas infrastructure. 97 Figure 5 to 3. Typical SCADA arrangement for oil operations. 99 Figure 5 to 4. SCADA integrates control of remote natural gas facilities. 100 Figure 5 to 5. Examples of oil interdependencies. 102 Figure 5 to 6. Examples of natural gas interdependencies. 102 Figure 6 to 1. 2003 Class I railroad tons originated. 107 Figure 6 to 2. CSXT train dispatch center. 108 Figure 6 to 3. Typical block signal control equipment enclosure. 110 Figure 6 to 4. Grade crossing shelter and sensor connection. 110. Figure 6 to 5. Modern locomotive functional block diagram. 111. Figure 6 to 6. A typical signalized intersection. 113 Figure 6 to 7. Container cranes and stored containers. 117 Figure 6 to 8. RTG at Seagirt Marine Terminal. 118 Figure 6 to 9. Handheld wireless data unit. 119. Critical national infrastructures. Table of contents V. Figure 6 to 10. Truck control station. 119 Figure 6 to 11. An ARTCC operations room. 122 Figure 9 to 1. A generic modern emergency services system. 148 Figure 10 to 1. From left to right, the orange, teak, kingfish, checkmate, and starfish high-altitude nuclear tests conducted in 1958 and 1962 by the United States near Johnston Island in the mid-Pacific. 159 Figure 10 to 2. Satellite orbits illustrated. 159 Figure 10 to 3. Areas of space irradiated by photons and neutrons. 160 Figure 10 to 4. Naturally occurring belts, Van Allen belts, of energetic particles. Persistently trapped in the geomagnetic field are illustrated. 161. Figure 10 to 5. Schematic diagram of relative intensities of trapped fluxes from two identical high-altitude nuclear detonations. 161 Figure 10 to 6. Satellites remaining after a 10, Montana burst over Lake Superior. 167 Figure 10 to 7. Satellite ground-based receiver outage time after a 10, Montana burst over Lake Superior. 167 Figure 10 to 8. HEO satellite exposure to trapped radiation produced by events 11, 17, and 21. 168. List of tables. Table 3 to 1. Telecommunications equipment tested. 73 Table 10 to 1. Trial nuclear events. 163 Table 10 to 2. Analysis of satellites. 164 Table 10-3. Probability that satellites suffer damage by direct exposure to X-rays. 165 Table 10-4. Trial events in Group 1. 165 Table 10-5. Trial events in Group 2. 166 Table 10-6. Trial events in Group 3. 166. Critical national infrastructures. Preface 6. Preface. The physical and social fabric of the United States is sustained by a system of systems, a complex and dynamic network of interlocking and interdependent infrastructures, critical national infrastructures, whose harmonious functioning enables the myriad actions, transactions, and information flow that undergird the orderly conduct of civil society in this country. The vulnerability of these infrastructures to threats, deliberate, accidental, and acts of nature, is the focus of greatly heightened concern in the current era, a process accelerated by the events of 9/11 and recent hurricanes, including Katrina and Rita. This report presents the results of the Commission's assessment of the effects of a high-altitude electromagnetic pulse, EMP, attack on our critical national infrastructures, and provides recommendations for their mitigation. The assessment is informed by analytic and test activities executed under Commission sponsorship, which are discussed in this volume. An earlier executive report of the Commission to assess the threat to the United States from electromagnetic pulse, EMP, Volume 1, Executive Report, 2004, provided an overview of the subject. The electromagnetic pulse generated by a high-altitude nuclear explosion is one of a small number of threats that can hold our society at risk of catastrophic consequences. The increasingly pervasive use of electronics of all forms represents the greatest source of vulnerability to attack by EMP. Electronics are used to control, communicate, compute, store, manage, and implement nearly every aspect of United States, U.S., civilian systems. When a nuclear explosion occurs at high altitude, the EMP signal it produces will cover the wide geographic region within the line of sight of the detonation point. This broadband, high-amplitude EMP, when coupled into sensitive electronics, has the capability to produce widespread and long-lasting disruption and damage to the critical infrastructures that underpin the fabric of U.S. society. Because of the ubiquitous dependence of U.S. society on the electrical power system, its vulnerability to an EMP attack, coupled with the EMP's particular damage mechanisms, creates the possibility of long-term, catastrophic consequences. The implicit invitation to take advantage of this vulnerability, when coupled with increasing proliferation of nuclear weapons and their delivery systems, is a serious concern. A single EMP attack may seriously degrade or shut down a large part of the electric power grid in the geographic area of EMP exposure effectively instantaneously. There is also a possibility of functional collapse of grids beyond the exposed area, as electrical effects propagate from one region to another. The time required for full recovery of service would depend on both the disruption and damage to the electrical power infrastructure and to other national infrastructures. Larger affected areas and stronger EMP field strengths will prolong the time to recover. Some critical electrical power infrastructure components are no longer manufactured in the United States, and their acquisition ordinarily requires up to a year of lead time in routine circumstances. Damage to or loss of these components could leave significant parts of the electrical infrastructure out of service for periods measured in months to a year or more. There is a point in time at which the shortage or exhaustion of sustaining backup systems. For example, a nuclear explosion at an altitude of 100 kilometers would expose 4 million square kilometers, about 1.5 million square miles, of Earth's surface beneath the burst to a range of EMP field intensities. Critical national infrastructures. Preface 7. Including emergency power supplies, batteries, standby fuel supplies, communications, and manpower resources that can be mobilized, coordinated, and dispatched, together lead to a continuing degradation of critical infrastructures for a prolonged period of time. Electrical power is necessary to support other critical infrastructures, including supply and distribution of water, food, fuel, communications, transport, financial transactions, emergency services, government services, and all other infrastructures supporting the national economy and welfare. Should significant parts of the electrical power infrastructure be lost for any substantial period of time, the Commission believes that the consequences are likely to be catastrophic, and many people may ultimately die for lack of the basic elements necessary to sustain life in dense urban and suburban communities. In fact, the Commission is deeply concerned that such impacts are likely in the event of an EMP attack unless practical steps are taken to provide protection for critical elements of the electric system and for rapid restoration of electric power, particularly to essential services. The recovery plans for the individual infrastructures currently in place entirely assume, at worst, limited upsets to the other infrastructures that are important to their operation. Such plans may be of little or no value in the wake of an EMP attack because of its long-duration effects on all infrastructures that rely on electricity or electronics. The ability to recover from this situation is an area of great concern. The use of automated control systems has allowed many companies and agencies to operate effectively with small workforces. Thus, while manual control of some systems may be possible, the number of people knowledgeable enough to support manual operations is limited. Repair of physical damage is also constrained by a small workforce. Many maintenance crews are sized to perform routine and preventive maintenance of high-reliability equipment. When repair or replacement is required that exceeds routine levels, arrangements are typically in place to augment crews from outside the affected area. However, due to the simultaneous, far-reaching effects from EMP, the anticipated augmenters likely will be occupied in their own areas. Thus, repairs normally requiring weeks of effort may require a much longer time than planned. The consequences of an EMP event should be prepared for and protected against to the extent it is reasonably possible. Cold War-style deterrence through mutual assured destruction is not likely to be an effective threat against potential protagonists that are either failing states or transnational groups. Therefore, making preparations to manage the effects of an EMP attack, including understanding what has happened, maintaining situational awareness, having plans in place to recover, challenging and exercising those plans, and reducing vulnerabilities, is critical to reducing the consequences, and thus probability, of attack. The appropriate national-level approach should balance prevention, protection, and recovery. The Commission requested and received information from a number of federal agencies and national laboratories. We received information from the North American Electric Reliability Corporation, the President's National Security Telecommunications Advisory Committee, the National Communications System, since absorbed by the Department of Homeland Security, the Federal Reserve Board, and the Department of Homeland Security. Early in this review it became apparent that only limited EMP vulnerability testing had been accomplished for modern electronic systems and components. To partially remedy this deficit, the Commission sponsored illustrative Critical National Infrastructures. Preface 8. Testing of current systems and infrastructure components. The Commission's view is that the federal government does not today have sufficiently robust capabilities for reliably assessing and managing EMP threats. The United States faces a long-term challenge to maintain technical competence for understanding and managing the effects of nuclear weapons, including EMP. The Department of Energy and the National Nuclear Security Administration have developed and implemented an extensive nuclear weapons stockpile stewardship program over the last decade. However, no comparable effort was initiated to understand the effects that nuclear weapons produce on modern systems. The Commission reviewed current national capabilities to understand and to manage the effects of EMP and concluded that the country is rapidly losing the technical competence in this area that it needs in the government, national laboratories, and industrial community. An EMP attack on the national civilian infrastructures is a serious problem, but one that can be managed by coordinated and focused efforts between industry and government. It is the view of the Commission that managing the adverse impacts of EMP is feasible in terms of time and resources. A serious national commitment to address the threat of an EMP attack can develop a national posture that would significantly reduce the payoff for such an attack and allow the United States to recover in a timely manner if such an attack were to occur. Critical national infrastructures. Acknowledgements 9. Acknowledgements. The Commission is pleased to acknowledge the support of its staff, whose professionalism and technical competence have contributed substantially to this report. Dr. George Baker, Dr. Yvonne Bartoli, Mr. Fred Selek, Dr. Edward Conrad, Dr. Michael Frankel, Dr. Ira Kohlberg, Dr. Rob Mahoney, Dr. Mitch Nikolic, Dr. Peter Vincent Pry, Dr. James Skouras, Dr. James Silk, Ms. Shelley Smith, Dr. Edward Toton. The Commission additionally acknowledges the technical and scientific contributions of Dr. William Radesky, Dr. Jerry Lubel, Mr. Walter Scott, Mr. Paul F. Spraggs, Dr. Al Constantine, Dr. Jerry Gertman, Dr. Vic Van Lint, Dr. John Kappenman, Dr. Phil Morrison, Mr. John Bombard, Mr. Bron Sakotas, Mr. David Ambrose, Dr. Bill White, Dr. Yakov Hames, Dr. Rebecca Ettinger, Ms. Rachel Balsam, and Mr. Chris Baker. The Commission also acknowledges the cooperation and assistance of Ms. Linda Berg, Dr. Dale Klein, former Assistant to the Secretary of Defense, Nuclear, Chemical, and Biological Matters, the leadership of the Defense Threat Reduction Agency, and its Commission liaison, Ms. Joan Pierre, Dr. Don Linger, Senior Scientist at the Defense Threat Reduction Agency, Dr. David Stout of the Naval Surface Warfare Center Dahlgren, Dr. Michael Bernardine of Los Alamos National Laboratory, and Dr. Tom Thompson and Dr. Todd Hoover of the Lawrence Livermore National Laboratory. We also acknowledge the cooperation of the intelligence community, IC. The Commission was ably supported by the contracted research activities of the following organizations: the National Nuclear Security Administration's laboratories, Lawrence Livermore National Laboratory, Los Alamos National Laboratory, Sandia National Laboratory, Argonne National Laboratory, Idaho National Laboratory, Naval Surface Warfare Center Dahlgren, the Institute for Defense Analyses, JASER/Titan, Meditech Corporation, Science Applications International Corporation, Telcordia Technologies, Mission Research Corporation, and the University of Virginia Center for Risk Management of Engineering Systems. Critical National Infrastructures. Chapter 1. Infrastructure Commonalities 1. Chapter 1. Infrastructure Commonalities. The physical and social fabric of the United States is sustained by a system of systems. A complex and dynamic network of interlocking and interdependent infrastructures, critical national infrastructures, whose harmonious functioning enables the myriad actions, transactions, and information flow that undergird the orderly conduct of civil society in this country. The vulnerability of these infrastructures to threats, deliberate, accidental, and acts of nature, is the focus of heightened concern in the current era, a process accelerated by the events of 9/11 and recent hurricanes, including Katrina and Rita. This volume focuses on a description of the potential vulnerabilities of our critical national infrastructures to electromagnetic pulse, EMP, insult, and to that end, the chapters in this document deal individually with the EMP threat to each critical infrastructure separately. However, to set the stage for understanding the potential threat under conditions, in which all infrastructures are under simultaneous attack, it is important to realize that the vulnerability of the whole, of all the highly interlocked critical infrastructures, may be greater than the sum of the vulnerability of its parts. The whole is a highly complex system of systems, whose exceedingly dynamic and coordinated activity is enabled by the growth of technology, and where failure within one individual infrastructure may not remain isolated, but, instead, induce cascading failures into other infrastructures. It is also important to understand that not only mutual interdependence, and hence new vulnerabilities, may be enabled by technology advances, but also technologies that have facilitated this growing interdependence may be common across the many individual infrastructures. In particular, the Commission thought it important to single out the growth and common infrastructural infiltration of one particular transformative technology, the development of automated monitoring and control systems, the ubiquitous robots of the modern age known as supervisory control and data acquisition, SCADA, systems. This opening chapter thus focuses on a more detailed description of these two aspects of modern infrastructures, control systems, and mutual interdependence that are common to all and which the Commission believes provide context and insight for understanding sources of vulnerability in all the nation's infrastructures to EMP attack. SCADA systems. Introduction SCADAs have emerged as critical and growing elements of a quietly unfolding industrial revolution spurred by the computer age. The accelerating penetration of SCADA systems, along with their electronic cousins, digital control systems, DCS, and programmable logic controllers, PLC, as critical elements in every aspect of every critical infrastructure in the nation, is both inevitable and inexorable. While conferring economic benefit and enormous new operational agility, the growing dependence of our infrastructures on these omnipresent control systems represents a new vector of vulnerability in the evolving digital age of the 21st century, such as cybersecurity. Such issues remain as a matter for high-level concern and attention today. High-altitude EMP focuses our attention toward another potential vulnerability of these systems, and one with potentially vastly expanded consequences. Critical national infrastructures. Chapter 1. Infrastructure commonalities 2. What is a SCADA? SCADAs are electronic control systems that may be used for data acquisition and control over large and geographically distributed infrastructure systems. They find extensive use in critical infrastructure applications such as electrical transmission and distribution, water management, and oil and gas pipelines. SCADA technology has benefited from several decades of development. It has its genesis in the telemetry systems used by the railroad and aviation industries. In November 1999, San Diego County Water Authority and San Diego Gas and Electric companies experienced severe electromagnetic interference to their SCADA wireless networks. Both companies found themselves unable to actuate critical valve openings and closings under remote control of the SCADA electronic systems. This inability necessitated sending technicians to remote locations to manually open and close water and gas valves, averting, in the words of a subsequent letter of complaint by the San Diego County Water Authority to the Federal Communications Commission, a potential catastrophic failure of the aqueduct system. The potential consequences of a failure of this 825 million gallon per day flow rate system ranged from spilling vents at thousands of gallons per minute to aqueduct rupture with ensuing disruption of service, severe flooding, and related damage to private and public property. The source of the SCADA failure was later determined to be radar. Operated on a ship 25 miles off the coast of San Diego. The physical form of a SCADA may differ from application to application, and from one industry to another, but generally they all share certain generic commonalities. A SCADA system physically bears close resemblance to the internals of a generic desktop personal computer. Typically, it might contain familiar-appearing circuit boards, chips of various sorts, and cable connectors to the external world. The cable connectors, in turn, may be connected, perhaps quite remotely, to various sensor systems that are the SCADA's eyes and ears, as well as electronic control devices by which the SCADA may issue commands that adjust system performance. Figure 1:1 provides an example of a particular SCADA controller that is representative of many such systems. Figure 1:1. Typical SCADA architecture. Critical national infrastructures. Chapter 1. Infrastructure commonalities 3. One major function of a SCADA, the data acquisition part of the acronym, is to provide a capability to automatically and remotely monitor the operating state of a physical system. It accomplishes this monitoring by providing an ongoing reporting of parameters that either characterize the system's performance, such as voltage or currents developed in an electric power plant, flow volume in a gas pipeline, and net electrical power delivered, or received by a regional electrical system, or by monitoring environmental parameters, such as temperature, in a nuclear power plant, and sending an alarm when prescribed operating conditions are exceeded. The supervisory control function of a SCADA reflects the ability of these devices to actively control the operation of the system by adjusting its output. For example, should an electrical generating plant fail through loss of a critical hardware component, or industrial accident, the monitoring SCADA will detect the loss, issue an alert to the appropriate authorities, and issue commands to other generating plants under its control to increase their power output to match the load again. All these actions take place automatically, within seconds, and without a human being involved in the immediate control loop. A typical SCADA architecture for the electric power industry may consist of a centralized computer, the Master Terminal Unit, MTU, communicating through many Remote Terminal Unit, RTU, subsystems, as illustrated in Figure 1 to 2. The RTUs are used in remote, unmanned locations where data acquisition and control tasks must be performed. Examples of typical RTU data acquisition actions include processing signals from sensors, such as thermocouples, voltage sensors, or power meters, and reporting the state of equipment, such as switch and circuit breaker positions. Typical control actions include starting and stopping motors, and controlling valves and circuit breakers. Figure 1 to 2. Generic SCADA architecture DCSs share many functional and physical hardware similarities with SCADA systems. A DCS typically will be used to control automated processes at a single location, such as Critical National Infrastructures. Chapter 1. Infrastructure Commonalities for an oil refinery or a chemical plant. In contrast, a SCADA typically might be sited in an environment with dispersed assets, where real-time situational awareness from remote locations is a key element of centralized control. Most DCS installations control complex, dynamic systems that would be difficult or impossible to control in a safe or economical manner using only manual control. Even a relatively straightforward process, such as electrical power generation using a conventional steam cycle, requires highly complex systems to maximize efficiency, while maintaining safety and environmental protection. For example, control systems in a steam generating plant would include parameters such as generator speed, generator lubrication oil pressure, excitation current and voltage output, feed water pressure and boiler steam drum level, and air box pressure and rate of combustion. Upset of these control points has the potential to cause severe physical damage. A case in point is the boiler endpoints of combustion and circulation. Normally, the control system would first reach the endpoint of combustion, limit of air and fuel, adding energy into the boiler, and, thus, prevent any thermal damage to the boiler. If the control system is upset, it potentially could reach the endpoint of circulation, maximum rate of steam generation, or endpoint of carryover, maximum rate at which water is not carried out of the boiler, before the endpoint of combustion. This situation would cause thermal damage to the boiler tubes, or physical damage to steam turbine blades. Normally, a PLC is used to control actuators or monitor sensors, and is another piece of hardware that shares many physical similarities to SCADAs, and is often found as part of a larger SCADA or DCS system. The SCADA, DCS, and PLC systems all share electronic commonalities, and, thus they share intrinsic electronic vulnerabilities as well. SCADA systems, however, tend to be more geographically disposed and exposed. Our subsequent discussion focuses on SCADAs. When exposure or unprotected cable connectivity is an issue, the discussion should be considered to pertain to both PLC and DCS as well. See Figure 1 to 3. Figure 1 to 3. PLC switch actuator EMP interaction with SCADA system components, by their nature, are frequently situated in remote environments and operate without proximate human intervention. Although their critical electronic elements usually are contained within some sort of metallic box, the enclosures. Critical national infrastructures. Chapter 1. Infrastructure commonalities 5. Service as a protective Faraday cage is typically minimal. Generally, such metallic containers are designed only to provide protection from the elements and a modicum of physical security. They typically are not designed to protect the electronics from high-energy electromagnetic pulses that may infiltrate either from the free field or from the many antennae cable connections that may compromise electromagnetic integrity. The major concern for SCADA vulnerability to EMP is focused on the early time E1 component of the EMP signal. This is because, even in the power industry, SCADA systems generally are not directly coupled electrically to the very long cable runs that might be expected to couple to a late-time E3 signal. To come to grips with the potential vulnerability of our critical national infrastructures caused by a threat to these ubiquitous SCADA control systems, we must first develop a sense of the vulnerability of the underlying hardware components themselves. To this end, the EMP Commission sponsored and funded a series of tests of common SCADA components in a government-owned EMP simulator, see Figure 1-4. The simulation testing provided an opportunity to observe the interaction of the electromagnetic energy with equipment in an operational mode. Because the simulator did not completely replicate all characteristics of a threat-level EMP environment, observed test results can be related to the system's response in more realistic scenarios through analysis and judgment based on coupling differences between the simulated and real-world cases. Figure 1-4. EMP simulator with test structures and internal electronics. The Commission consulted with experts from industry groups associated with the North American Electric Reliability Corporation, NERC, and by site and market surveys to identify representative control systems for testing. A test matrix was developed that reflected electronic control technologies employed in power generation, power distribution, pipeline distribution, and manufacturing plants. Some test items assessed in this effort are shown in Figure 1-5. Critical National Infrastructures. Chapter 1. Infrastructure Commonalities 6. Figure 1-5. Some of the electronic control systems exposed in test facility EMP simulation testing. In this section, we provide a brief summary of the results of illuminating electronic control systems in the simulator. The detailed results of the simulation test program are documented separately in reports sponsored by the Commission. In Chapter 2, we provide a more complete description of the test methodology, in which we discuss testing carried out during assessment of the EMP vulnerability of the electric grid. Many of the control systems that we considered achieved operational connectivity through Ethernet cabling. EMP coupling of electrical transients to the cables proved to be an important vulnerability during threat illumination. Because the systems would require manual repair, their full restoration could be a lengthy process. A simple model of 4 Ethernet cables from a router to 4 personal computers, PC, was generated to quantify the impact of cable length. The configuration of this model is shown in Figure 1-6. The results of the analysis indicate that the coupling to the 200 feet of Ethernet line is roughly 7 times the transient level on the 25-foot line measured during the test program. The testing and analysis indicate that the electronics could be expected to see roughly 100 to 700 ampere current transients on typical Ethernet cables. Effects noted in the EMP testing occurred at the lower end of this scale. The bottom line observation at the end of the testing was that every system tested failed when exposed to the simulated EMP environment. The failures were not identical from system to system or within a system. For example, a device with many input-output ports might exhibit degraded performance on one port, physical damage on another, and no effect on a third. Control units might report operating parameters at variance with their post-illumination reality or fail to control internal flows. The Commission considered the implications of these multiple simultaneous control system failures to be highly significant as potential contributors to a widespread system collapse. Impact of SCADA vulnerabilities on critical infrastructures. Historical insight based on the testing and analysis outlined in the previous section, we estimate that a significant fraction of all remote control systems within the EMP-affected area will. Critical national infrastructures. Chapter 1. Infrastructure Commonalities 7. IBM compatible, IBM compatible, IBM compatible, IBM compatible. Router. 25-050-0 Figure 1 to 6. Physical model used to quantify coupling to different cable lengths in a hypothetical local area network, LAN, experienced some type of impact. As the test results were briefed to industry experts at NERC and the Argonne National Laboratory, it became apparent that even minor effects noted during the testing could significantly affect the processes and equipment being controlled. Putting together a complete analysis for complex processes associated with infrastructure systems is extremely difficult. Developing the ability to analyze or model these impacts is beyond the scope of this effort. To provide insight into the potential impact of these EMP-induced electronic system malfunctions, one can consider the details of historical events. In these cases, similar, and arguably less severe, system malfunctions have produced consequences in situations that are far too complex to predict beforehand using a model or analysis. Another important observation is that these incidents are seldom the result of a single factor. Rather, they are a combination of unexpected events that, only in hindsight, are easily related to the impact. This is not surprising given the complexity of the systems involved. Before considering the historical database, it is important to remember that historical examples, although important for the insight they provide into the dependence of a functioning modern infrastructure on its automated eyes, ears, and remote control layers, do not adequately capture the scale of the expected EMP scenario. In the latter, it is not one or a few SCADA systems that are malfunctioning, the typical historical SCE scenario, but large numbers, hundreds or even thousands, with some fraction of those rendered permanently inoperable until replaced or physically repaired. Significant historical events that provide insight into the potential impact of damage or upset to control systems include Hurricane Katrina, the 1996 Western States blackout, the August 14, 2003, Northeast blackout, a geomagnetic storm in 1989, the June 10, 1999, Bellingham pipeline incident, the August 19, 2000, Carlsbad pipeline incident, the July 24, 1994, Pembroke, United Kingdom, refinery incident, and a Netherlands electromagnetic interference, EMI incident. The following paragraphs discuss the relevance of 4 of these incidents to an EMP event. The other 4 incidents, Hurricane Katrina, the Western States blackout, the August 14, 2003, blackout, and the 1989 geomagnetic storm, are described in Chapter 2, which is dedicated to a discussion of EMP effects on the electric power grid. Bellingham pipeline incident. On June 10, 1999, one of the Olympic pipelines transporting gasoline ruptured in the Whatcom Falls Park area of Bellingham, Washington. About 250,000 gallons of gasoline from the pipeline entered the Hannah and Whatcom Creeks, where the fuel ignited, resulting in 3 fatalities and 8 injuries. In addition, the banks of the creek were destroyed over a 1.5-mile section, and several buildings AJA sent to the creek were severely damaged. Critical national infrastructures. Chapter 1. Infrastructure commonalities 8. Causes included improperly set relief valves, delayed maintenance inspections, and SCADA system discrepancies. The effects all came together at the same time that changes in pipeline operations were occurring. Given the wide area of an EMP, it is conceivable that some of the pipelines affected could also suffer from poor maintenance. The electronic disturbance of an EMP event could be expected to precipitate SCADA failures and the ensuing loss of valve controls. Carlsbad pipeline incident. On August 19, 2000, an explosion occurred on one of 3 adjacent large natural gas pipelines near Carlsbad, New Mexico, operated by the El Paso Natural Gas Company. The pipelines supply consumers and electric utilities in Arizona and Southern California. 12 people, including 5 children, died as a result of the explosion. The explosion left an 86-foot-long crater. After the pipeline failure, the Department of Transportation's Office of Pipeline Safety, OPS, ordered the pipeline to be shut down. The explosion happened because of failures in maintenance and loss of situational awareness, conditions that would be replicated by data acquisition disruptions caused by an EMP event. Pembroke Refinery Incident. On July 24, 1994, a severe thunderstorm passed over the Pembroke Refinery in the United Kingdom. Lightning strikes resulted in a 0.4-second power loss and subsequent power dips throughout the refinery. Consequently, numerous pumps and overhead fin-fan coolers tripped repeatedly, resulting in the main crude column pressure safety valves lifting and major upsets in the process units in other refinery units, including those within the fluid catalytic cracking (FCC) complex. There was an explosion in the FCC unit, and a number of isolated fires continued to burn at locations within the FCC, but